Hello, good morning. Okay, let's start the class. So today will be an extra lecture. So all the materials that we are discussing today won't be appearing in the exam. So let's see. Okay, so we are going to talk about relation. Okay, and then we will define what is meant by binary relations, and then there are different ways of representing binary relations, and then we define a concept called closures. And relation is something that is like what we are going to do, like algebra. We are going to talk about some properties of sets, such that if certain set follows this property, then it will have the same or similar behavior. So this is the purpose of studying relation. Firstly, let us see this name, Cartesian product. Suppose that A and B are two sets. The Cartesian product of A and B, denoted by A times B, is the set of all pairs of little a, little b, such that the little a comes from big A and the little b comes from big B. So we call this the Cartesian product of A and B, or A times B. So for instance, we suppose that A is the set of numbers or labels 1, 2, 3, 4, 5, 6 up to 10, and then J, Q, K. And then B is the set of the suits of a standard deck of playing cards. So we have spades, we have hearts, we have diamond, and we have clubs. So B has 4 elements. Then the Cartesian product of A and B will be, it contains all the 52 cards in the deck. So it has 1 spade, 2 spade, 3 spade, up to king of clubs. Okay. Now notice that Cartesian product is an ordered arrangement of A and B. So A times B in general is not the same as B times A. They're the same only if what? If A and B are the same, this is one of the case, or if one of these A and B is an empty set, then in that case A times B will be an empty set. So in general, so you can see that A times B is 1 spade, 2 spade, 3 spade in this example, but then B times A will contain a different set of items. It will be spade 1, spade 2 up to clubs of king. Okay. The concept of Cartesian product can be generalized to be defined on more than 2 sets. So suppose that A1, A2 up to AK, they are K sets. So we can define A1 times A2 times A3 up to AK to be the set of all ordered pairs with little a1, a2 up to ak, such that each of these little aj comes from the big aj. Okay, so for instance, if aj denotes the set of all real numbers, then a1 times a2 times a3 will be the set of all 3D Euclidean points, where each point has coordinate chosen from a real number. So this will be the Euclidean space, real to the power 3. Okay? Now we are ready to talk about the new concept called relation. So a binary relation from A to B is simply a subset of the Cartesian product of A times B. So it is nothing special. A subset of a Cartesian product is called a relation. So for instance, using our previous example, we have A to be the possible ranks, 1, 2, 3 up to king, and B to be the set containing all the suits. Then we can define a certain subset. For instance, let's call it space. Space contains all the case where the little b part is spade. So we have 1 spade, 2 spade, 3 spade, so up to king of spades. So this is a subset of A times B, and we call this a binary relation. And similarly, we can define a k-ary relation. So this relation thing has real life application. So in real life, we have something called a database system, which store the records of something that we want to keep. So for instance, a bank will store records of the customers. A shop will store records of the transactions that it made, and so on and so forth. So for a bank, a customer could be represented by a tuple here. Maybe it has the customer's name, the customer's ID, the customer's different, how many accounts it has, the birthdays, and so on and so forth. So each customer will be corresponding to a point or a particular item in the Cartesian product. And then there are millions or okay, so to manage the database of the bank or the database of a shop, then we are going to use relation naturally to do so. So if you study database design later when you are in year 3 or year 4, then you will come across relation again. So let's see, this is an example. So for instance, suppose that L denotes the set of tuples x, y, z such that 2x plus 3y plus z is equal to 0, and x, y, z, they are real numbers. So L is a subset of the Cartesian product R times R times R. Is that okay? And this one, is it correct? I don't know. So this one should correspond to some geometric object in the 3D space. So I call it a line. I'm not sure whether it is a line or not. Maybe this is a plane. This should be a plane. Yeah. But in any case, L is a subset of R times R times R, and then this is a theory relation or a ternary relation. But what we are going to talk about in this lecture is special types of relation. We look at relation from a set A to itself, so that we are looking at the subset of the Cartesian product A times A. And in such a case, the relation is called a binary relation on A, okay, rather than a binary relation of A to B, because it is of A to A. So we have something special on A. For instance, suppose that A is the set of integers, and then we can define a subset R to be collecting all the tuples AB such that A minus B is greater than or equal to 10. So R is a subset of A times A, and this is a binary relation on A. Okay, now we want to introduce some special types of binary relation. So the first one is simple. If a binary relation R contains AA for every little a in the big subset A, then this relation is called a reflexive relation. So reflexive is like you see your reflection in a mirror. So whenever any little item A of the big set A, you have AA in R, then in that case, the relation is a reflexive relation. So this is a description of whether a relation has this property or not. So for instance, we have a couple of examples here. We want to see whether the following relations are reflexive or not. So the first one is AB such that A minus B is greater than or equal to 10. A, B are integers. So we can check easily that if I have AA, so for instance, 1, 1, is 1, 1 contained here, is 2, 2 contained here, and so on and so forth. And obviously, 1, 1 or AA is not in R because A minus A is equal to 0. It is not greater than or equal to 10. So in that case, AA in general is not contained in R. So this R here is not reflexive. And the next one, S, contains all the tuples AB such that A is smaller than or equal to B. And in that case, we will see that for any A is really smaller than or equal to A. So in that case, this big S contains AA for every possible item A. And in that case, S is a reflexive relation. For T, it is containing tuples of AB such that A is smaller than B. And we see that A is not smaller than A in general. So in that case, T doesn't contain every AA. So T is not reflexive. And U is something special. Okay, not talking about integers anymore. So we have X and Y. So X and Y, they are days in April of 2013. So X and Y can range from 1st of April, 2nd of April, up to the 30th of April of 2013. So there are 30 items in the possible item set that we can choose from. And then we say that X and Y are on the same weekday. So for instance, 1st of April and 8th of April, they are on the same weekday. So we will say 1st of April and 8th of April, they are contained in big U. So we will see that for any x, xx is in U. Yeah, because 1st of April is on the same weekday as 1st of April, 2nd of April is on the same weekday as 2nd of April, and so on and so forth. So in that case, we see that U is also a reflexive relation. So reflexive is easy to remember. It is you see yourself inside the mirror. So it talks about only one item and whether the item is related to itself. So if we see AA is in R, so we will say that A is related to A in big R. Now, the next type of relation we want to talk about is symmetric relation. So symmetric relation requires that whenever AB is in R, then BA has to be in R. Okay, so it doesn't require that for every AB it has to be in R. It just has this condition: whenever AB is in R, BA is also in R. So another way to say this is whenever A is related to B, then B is also related to A. So that's why we call this symmetric. Symmetric talks about two persons and then they are somehow equal in the positions. So let's see some examples. So for instance, AB contains the case, so we have R contains all the tuples AB where A minus B is greater than or equal to 10. Now we see that this is not symmetric because as an example, we see that 10, 0 is in R. Yeah, because 10 minus 0 is really greater than or equal to 10, but 0, 10 is not. So R is not symmetric. So whenever AB is in R, we need to have BA in R for it to be symmetric, but in this case, it is not. Now, how about this one? If A is smaller than or equal to B, then B normally is not smaller than or equal to A. So this S is also not symmetric. T is also not symmetric. And then U is symmetric. So whenever X and Y are on the same weekday, Y and X will also be on the same weekday. Now, symmetric relation, here I should specify that the AB that we talk about, they are different items. So we don't require, yeah, but normally, yeah, AB, if AA is already in R, then it's also in R. Okay, so here for symmetric relation, so we define like this. Okay. And then another one is called, don't be confused, but the other one is called anti-symmetric. So anti-symmetric says that if AB is in R, then BA cannot be in R unless A is equal to B. So for anti-symmetric relation, we will forget all the cases of the reflexive case, AA. But whenever A and B are different, if A is related to B, then B cannot be related to A. So if this is holding, if this is true for every AB that we see, then this relation is called anti-symmetric. So for instance, R contains AB where A minus B is greater than or equal to 10, then we will see that this is anti-symmetric. Because when A minus B is greater than or equal to 10, then B minus A cannot be greater than or equal to 10. So R is an anti-symmetric relation. S. So here, S contains AB where A is smaller than or equal to B, we see that A is smaller than or equal to B in general implies that B cannot be smaller than or equal to A, except AB are the same. But we don't care the case where AB are the same. So when AB are different and A is smaller than or equal to B, then B cannot be smaller than or equal to A. So this S is also anti-symmetric. How about T? T is obvious, so when A is smaller than B, B cannot be smaller than A, so T is anti-symmetric. And how about U? If X and Y are on the same weekday, then Y and X must be on the same weekday. So in that case, it is not anti-symmetric. Okay. Now notice that symmetric and anti-symmetric is not something that is contradicting. We can have a relation that is at the same time symmetric and also anti-symmetric. So for instance, an empty set is a relation that is both symmetric and anti-symmetric. Is that okay? Or if we just have a set of relation that contains AA for every item A, then this relation is reflexive, and then because it doesn't have anything that is A is different from B, automatically this is symmetric and it is also anti-symmetric. Okay? And then the third case, so we have defined reflexive, symmetric, anti-symmetric. So a fourth type is called transitive. Transitive says if A is related to B and B is related to C, then we must have A is related to C. If this is holding for all the possible ABC, that we can write on the left-hand side here, if part, then in this case, this relation is called a transitive relation. So let's see. So first of all, is R a transitive relation? So for instance, suppose that I know AB is in R and BC is in R. So what does that mean? I know that A minus B is greater than or equal to 10, and I also know that B minus C is also greater than or equal to 10. Then is it true that A minus C will be greater than or equal to 10? Yeah, by simple algebra, yes. This is yes. So this R is a transitive relation. The next case is AB, where A is smaller than or equal to B. So if A is smaller than or equal to B, and B is smaller than or equal to C, is it true that A must be smaller than or equal to C? Now it is yes. So S is also a transitive relation. T, how about T? If A is smaller than B, B is smaller than C, is it true that A is smaller than C? Now T is also a transitive relation. Finally, how about U? So if X and Y, they are on the same weekday, and Y and Z, they are on the same weekday, is it true that X and Z, they are on the same weekday? Yeah, this is true. So U is also a transitive relation. Okay, so interestingly, the four relations that we are using as an example here, they are all transitive. Okay, now relation talks about, so it is always an item inside the relation is always a tuple. So how can we represent a binary relation? So there are two easy ways, or two easy most popular ways of doing so. The first one is we will use something called a matrix, a two-dimensional table to represent whether an item xy is contained in the relation or not. So here, suppose that the set of A is 1, 2, 3, 4, and R is a binary relation on A, which contains 1, 1, 1, 2, 2, 3, 2, 4, 3, 4, and 4, 2, these 6 tuples. Then in such a case, one way that we can represent this R is we draw a 4 by 4 table, and in the corresponding entry, we mark it by a tick. So in that case, 1, 1 is in R, so we have 1, 1, there is a tick. 1, 2, we have a tick. And then 2, 3, we have a tick. 2, 4, we have a tick. 3, 4, we have a tick. And 4, 2, we have a tick. So this is the matrix representation or the table representation of the relation. Easy, right? Okay, and another way is we can use a directed graph. So here again we are using the same set A and the same relation R. We have one, so we are going to use one vertex to represent one item in the original ground set A, and then use a directed edge to represent an item in the relation. So there's 1, 1. So it means that we are going to use a directed arrow pointing from 1 to 1. So this represents 1, 1. And 1, 2, we are using a directed edge pointing from 1 to 2. So we have 1 point to 2, 1, 2. This one, 2, 3. This arrow, 2, 4. This arrow, 3, 4. And this arrow, 4, 2. So it is really easy, right? So both representation of a binary relations have their different advantage. So we will see soon when we talk about a new concept called closure. Now, sometimes, given a binary relation, we can obtain a new relation R prime by adding items into R, such that R prime will have new properties. So here we emphasize that we can only add tuples into R. Okay. So for instance, suppose that R is 1, 1, 1, 2, 2, 3, 2, 4, 3, 4, and 4, 2. Now, if we add 2, 2, 3, 3, and 4, 4 into this R, we expand this R into some relation such that it is reflexive. Now, originally, this R is not reflexive. Now, this R is the example here. So to see that it is not reflexive, it is easy. So because 2, 2 is not contained in R, this is not reflexive. Or 3, 3 is not contained in R, this is not reflexive. But what we are going to do here is we add 2, 2, 3, 3, and 4, 4 into R. And in that case, we add a tick here, a tick here, a tick here. Then in that case, the new relation after adding the tuples will become reflexive. Okay? Now the closure is the idea is we want to find the smallest possible relation R prime that contains R as a subset. That means that we can only add tuples into R to make it into R prime because it has R as a subset. We add things to R such that R prime has a property P. So this property P could be reflexive, could be transitive, could be whatever property. And if this is the case, then it is called the closure of R with respect to P. So in the previous example, if we add these 3 ticks to R, then it makes R into a reflexive relation. And also, this is the smallest possible relation that contains R to make this into a reflexive relation. So this is called the reflexive closure of R. Is that okay? So, or closure of R with respect to the reflexive property, or we simply call it the reflexive closure of R. How about this one? Here, we have the relation R, and then we want to find the transitive closure. So what does that mean? We want to add enough tuples so that the new relation becomes transitive, and then we want to make sure that we add as few number of tuples as possible. And it turns out that the transitive closure must contain all the red ticks here. So this is a transitive closure of R. And actually, for the transitive closure, it is going to be a unique relation. Okay, there is no other transitive closure of R. There is only one single transitive closure of R. Okay, so why or how we can get a transitive closure? This is an interesting problem in theoretical computer science, or actually it has daily life application. Transitive closure, so how can we get it very efficiently? So remember, what is meant by transitive closure? We want to make this transitive, right? So for instance, I have 1, 2, I have 2, 3. In that case, in the transitive closure, I need to have 1, 3 because R contains 1, 2, R contains 2, 3. Then because 1, 2, and 2, 3 are there, then I need to have 1, 3, right? But how do I know that which ticks are necessary to be added? Okay, now here, one way is we can look at the directed graph representation. So the original R that we have, so this is an example. The original R contains all the edges, and each edge here in the directed graph represents, so it represents, and each edge is something that relates two vertices. Let's say 1 and 2 are related. It is because 1 can reach 2 in exactly one step. 2 can reach 3 in exactly one step. So we call this, so the R itself has this physical meaning. And then to compute the transitive closure, then because if we know 1, 2 is there, 2, 3 is there, we must have 1, 3. So we need to add 1, 3. So in that case, we know 1 can reach 2 in one step, 2 can reach 3 in one step, then that means that 1 can reach 3 in also 2 steps. Okay, so in that case, we are going to add the case where all the arrows from a vertex x to y, that x can reach y in exactly 2 steps. Then the meaning of a transitive closure is actually we want to find out the relationship between any two vertices such that whether x can reach y using the arrows in R in any number of steps. Okay, so here actually this is true, so you can verify by yourself. We claim that for a transitive closure, xy is in the transitive closure if and only if x can reach y in the directed graph. Okay, so one way to compute all these xy tuples is we compute all pairs of vertices where one can reach the other in exactly k steps. So R is represented as R to the power 1. From R to the power 1, we can easily get R to the power 2, R to the power 3, and so on and so forth until we do not add new edges. The resulting will be a transitive closure of R. So for instance, the original R is this one. So we add R square. R square is we add the red arrows such that each red arrow corresponds to the case where a vertex can reach the other in exactly 2 steps. So 1, 2, 2, 3. So I'll add 1, 3. Now, why am I adding these two? I'm adding these two. It is because why can I add these two? Let me see. So here I'm adding 2, 3. It is because let me see. Let me see. I'm getting stuck here. Oh, sorry. I'm adding this red arrow. It is because I have 3, 4, I have 4, 2. So I need to have 3, 2. If we do things carefully, we are going to add these red arrows one by one. So this is by adding R2. And then we can try to add R3 as well. So R3 is this one. So but we see that we are not adding new arrows from R2 to R3. We are adding this one, the green one. Yeah, why do we have a green one? Yeah, so we have this green one. It means that we can reach 3 to 3 in 3 steps. It is really true. 3 to 4, 4 to 2, 2 to 3. So that means that 3 can reach 3 in 3 steps. So we are adding this green arrow. But after this step, no new edges can be added. So we get the transitive closure. Okay, so here, the transitive closure can be computed in this way. When you study algorithm class later, let's say in year 3 or year 4, then you are going to find ways to compute the transitive closure quickly. And then the previous method that we introduced, it takes running time. If you have studied time complexity before, something like n to the power 3 times log n. It means that when there are n vertices in the graph, the number of computation steps is growing like n to the power 3 times log n, but there can be a faster algorithm that we know later. It can compute the transitive closure in n cubed. But in any case, the purpose for today's lecture is to introduce what is meant by all types of special relation and then what is meant by closure. Okay, so as long as you get the idea, then it is already good. Now I want to use, so this is the end for this lecture, but I want to spend a little bit more time to briefly talk about lecture 12. I'm not going to show the full details of these lecture slides, so I hope you can self-study by yourself if you are interested. But here, what I want to demonstrate is the power of studying relation or binary relation. So there are two special binary relations that are very important. One is called equivalence relation and the other is called partial ordering. Equivalence relation is a special relation that defines the concept of equal. So equal in our daily life is just like for integers, yeah, 1 is equal to 1, 2 is equal to 2, 3 is equal to 3, right? But you can also define some equal in different sense. For instance, we can define two numbers to be equal if two integers are equal if after division by 3 they have the same remainder. So we will say 1, 4, 7, 10, 13, and so on and so forth, they are equal. 2, 5, 8, 11, 14, they are equal. 3, 6, 9, 12, they are also equal. Okay, so here they are equal in the sense that they have equal remainders. Or for another instance, we can define equal like suppose that we have a map with cities and roads, and then the roads are bidirectional. So we can say 2 points, they are equal if one can reach the other by using the roads. So for instance, Taipei and Hsinchu is equal because we can reach them by roads. Hsinchu and Tainan, they are equal because we can reach Hsinchu and Tainan by roads. Taipei and Tainan is also equal because we can reach Taipei to Tainan by roads. But then Taipei and Kinmen or Taipei and Hong Kong, they are not equal because we cannot reach Taipei to Hong Kong by using roads. Okay. Now, equivalence relation will then have the same common behavior of things that we have equal as a concept. So what classifies a relation as an equivalence relation? So here we have for mathematicians, they find out that we can classify a relation as an equivalence relation if let me see how I can classify a relation as equivalence relation. Okay, so this is if a relation is at the same time reflexive, symmetric, and transitive. Now, if a relation has these three properties at the same time, this will be called an equivalence relation. And the relation itself has an interesting property. Using the equivalence relation, we can use it to classify the original items in A, whether they are equal or not. The equal items, let me see. So interestingly, with an equivalence relation, we can somehow group the items such that they are equal in the same group. And then we will find that it has a very nice property. All the equal items, they are going to form in the same group. And it will be in a different group with all the items in a different group. So for instance, suppose that we are talking about division by 3 having the same remainder. So we can use this relation to what? To group the numbers, to group the integers, such that they are equal to each other, and then we have exactly 3 groups. One group containing 1, 4, 7, 10, 13, another group contains 2, 5, 8, 11, 14, and then another group contains 3, 6, 9, and so on and so forth. And we will see that. We will see what? We will see that each of the original item must be in exactly one group, and then no item is going to be in different groups. So that's why we have now a concept of things that equal things are put together. And if such a case occurs, then we say that we have a partition of the original set. So we are making the original set into different parts, such that all the parts union together to form the original set, and then no two parts share a common item. So given an equivalence relation, we can get a partition of the original set. On the other hand, given any partition of an original set, there will be a corresponding equivalence relation. So that's why equivalence relation is having interesting property. It connects to the partition of a set. So if you're interested, take a look of this one by yourself. So this is the first type of special relation. Any equivalence relation shares this common property. It just needs the three little property: reflexive, symmetric, and transitive. Now, partial ordering is another one. Partial ordering means that we can order the items somehow. If a relation is a partial ordering, then it just needs to satisfy three properties. If it is reflexive, anti-symmetric, and transitive. So for partial ordering, so this is a corresponding partial ordering. So for partial order, so here I'm going to talk about two items. X and Y are related if X is a multiple of Y, something like this. So 2 and 1 is related, 3 and 1 is related, 6 and 2 is related, 6 and 3 is related. I'm missing some edge here. So 6 and 1 is also related. Okay, because 6 is a multiple of 1. 12 and 6 is related, 12 and 4 is related. So whenever, so this relation, you can check it carefully that it is reflexive, anti-symmetric, and also transitive. So whenever we have a relation like this, then this is called a partial ordering. And partial ordering can be represented nicely by something called a Hess diagram. You can check it check it by yourself later. But then partial ordering, you can have, so partial ordering appears naturally in daily life. For instance, suppose that we have a couple of, let me see if I have this example here. Yes. Yeah, this is a partial ordering that we can talk about. So here, this is about the wearing of clothes. So here, there is an order of wearing clothes. So we must wear the underwear before wearing the clothes. We must wear the clothes before we put on the tie. We must put on the tie before we put on the jacket, let's say. We must wear our clothes before we wear our trousers. But then before we wear our trousers, we need to wear our underpants, and so on and so forth. There is somehow orderings, or who should be done before which in this different tasks. But then some different tasks, there are no particular relationship. For instance, wearing shoes and wearing underpants, there's no, there is order. Yeah, shoes and pants, there are orders. But how about jacket and trousers? So there are no particular relation between jacket and trousers. So no one needs to be done before the other one. So they can be done in any order. And we can see that what should be done before which, it turns out that this is a partial ordering. Now, whenever we have a partial ordering, then we can prove that there is always a way that we can arrange the tasks one by one so that we don't hit any problem. So we can do what? We can use this ordering. Let's say we first wear our underwear, and then the clothes, and then the pants, and then the trousers, and so on and so forth. So that by using this ordering of performing the tasks, we don't hit any problem. We won't be wearing trousers before wearing the pants. So this is a very nice property of a partial order relation. So partial order relation describes the behavior between two tasks, and then given this partial order, there is a natural computation question whether we can arrange the items one by one so that all the items that should be done first are done first. And then it turns out that whenever it is a partial ordering, there must be at least one way of doing so. So this is something that is related to the discussion of relation. So I hope that you can find time to check it by yourself. Okay, yeah, having said a lot, so that's all for today. Yes, yeah, thank you for coming. And then next Monday will be our exam 3, and then next Wednesday, yeah, I will give out the solution of our exam 3. Okay, so that will be the end of the whole course. And yeah, I really thanks you a lot for joining the class. And and one little request. Okay, if you have not fill in the course evaluation in the academic information system, yeah, please help me to do so. Yeah, I want to get the response from you. Okay, that's all. Okay, thanks.